everyone. Our next speaker is Aravind. He is from University of Edinburgh. He is going to talk about a new medium of communication, that's a visible light. Usually we know the electromagnetic spectrum and the radio waves are the communication medium. He is going to present how visible light can be used for communication. Welcome, Aravind.
Hello, everyone. First of all, I would like to thank Ajish for introducing me here, and all URUK organizers who have done this wonderful event today with lots of interesting talks. So far, we have listened to stuff which is related to more related to social sciences or even medical science. I'm going to go in a bit different direction. So this is something related to technology. So I hope you guys will enjoy it and make it more of an interactive session. Okay, so thank you. So I'm going to begin. I'm going to talk about photons, right? So first thing, who can answer? Who can identify these two personalities here? Can somebody give a try? Yes? No. Yes. So that's Graham Bell. Well done. And the next one? No. Right. Okay. That's right. There's no previous data, so let's continue. Now can you try? Give it a try. There is previous data now. Marconi. Yes. That's Marconi. So Graham Bell and Marconi, and I think you guys know who they are and what they did for us. So I'm going to start from them. So first one is Alexander Graham Bell. He was born in Edinburgh in 1847, and he invented telephone. How many of you guys have used wired telephones? Wired telephones. Right. And how many of you guys haven't used wired telephones? Wired. So I can see some people who are not raising their hands. So I assume that they have not used wired telephones. So it's a thing of the past for many people now. So it's disappeared. How many of you have used something wireless? I think everybody, right? How many of you guys have smartphones or phones, mobile phones? All of you have. So, like Graham Bell, Marconi invented wireless telegraphy. So that was again 100 years ago. So all these things happened 100 years ago, and we have been using this technology for the last 100 years with not much change. The basic technology remains the same, but the aesthetics and the capacity has increased. So if we continue, what do you prefer, wired or wireless? Wireless, right? So that's convenience. So if you think about an user, if you think from an user's perspective, they always prefer wireless things, wireless headphones, wireless phones, wireless mics, right? Nobody likes wired mics these days. But from a technology perspective, wired things are convenient. It's easy to make wired devices or wired equipments, but it's very difficult to make wireless devices. Now, I've been working in the wireless area for some time, so we'll see where this is going to. So let's see how this works. Do you know how a mobile phone works, or when I'm speaking onto this microphone, how does it comes out of the speaker? Does anybody know the technology behind that? So what happens here is there is invisible radio waves going out of this phone to a receiver somewhere here, and that's been amplified and fed to the speaker. So that's a basic thing. So this was theorized by Maxwell in 1850s. And Heinrich Hertz, a German scientist, proved this on lab. He was able to create or generate radio waves on labs. This was first commercially done by Marconi. That's why he is famous, not Hertz is famous. You might have heard of Hertz, like megahertz, gigahertz, but you might not have heard that he is the one who first did a lab experiment where he produced radio waves in lab. But Marconi is a businessman, and he has a business mind or business acumen, so he was able to commercially sell this thing to the people, and he even won Nobel Prize for that. So how do we produce radio waves? You might have heard of things like charged particles, electrons, for example. You heard of electrons or protons or ions or things like that? All of them are charged particles. If you accelerate charged particles, they produce radio waves or electromagnetic waves. So what is an electromagnetic wave? It's a flow of electric field and magnetic field. You all know magnets, right? Magnets have magnetic fields around them. So these lights are glowing because we apply some electricity to that. So this electric field is a field of field produced by accelerated electrons. So accelerated electrons produce these sort of waves, which was theorized by Maxwell. So you can see that it's not just radio waves, it's a big spectrum. It's called electromagnetic spectrum. Our whole universe is filled with different types of waves from, including X-rays, gamma rays. Why do these things exist? Because that's how energy transfer happens in universe. If you want to transfer some sort of energy, you need to use one of these. So for example, when I'm speaking through this phone, there is an electrical energy being converted to sound energy. When you have lights here, it's actually electrical energy to light energy. You see the evolution here. So they both are radio transmitters. The first one is Marconi is one. It's probably much bigger than this cell phone here. You can see lots of antique things there, but it used to work. What it does is you can send Morse codes. It's primarily used by military to transmit coded information, when they are on the seas or when they are far away on a war field or something like that. So going ahead, before going to more details, I would like to tell you something about radio waves, because otherwise this presentation will not be useful. So a wave is a repeating pattern. So in our case, it's a repeating pattern of an electric field and a magnetic field. It has certain properties, wavelength. So it has crests and troughs, the valley and the peak and the valley, right? The dip and the peak. So the x-axis of this curve is time. So any peak to peak difference is the wavelength, and how many of such repeating cycles you have in 1 second is called hertz. So that's a frequency. So this waveform has one peak or one period in this time frame, so it's 1 hertz. So here you have 3 periods, 1, 2, and 3. So that's 3 hertz. So keep this in your mind. You don't need to think too much about it. Just these things, these phrases. Now that's the spectrum I've showed you before. What we have. So if you think about it, we have radio waves, which is used by lots of things. Your FM, AM radio. We have microwave. All the kitchen cooking you do. Whenever you turn on your microwave in your kitchen, you are generating microwaves. The microwave is what cooks your food. And you have infrared. You can't see that, but it's there. Whenever you feel hot, you have infrared radiation hitting your body. When you go out into the sun, you feel hot because sun is generating lots of infrared. So that's infrared. Then we have visible range. Visible, that's also electromagnetic waves. We say it visible because your eyes can detect that. So in previous Rajiv's presentation, he mentioned how our eyes are able to detect that. So that's the result of evolution, because we are evolved on sunlight. So over the years, a part of the spectrum we were able to detect. So other animals, for example, maybe like bats, probably are able to detect IR. Then you have ultraviolet, X-rays, and gamma rays. So different parts of this is the whole electromagnetic spectrum. So far. So how do we use? So I mentioned that we are using radio waves for communication or transmitting information. But how does that happen? How do they do that in real? So that's a waveform that we saw before, right? So lots of crests and troughs. It has certain frequency. So how do we transmit information? Whenever you're browsing internet, you usually it's a digital world, so you send zeros or ones, right? So it's transmitting zeros and ones. So a stream of zeros and ones. Whenever I'm browsing something on my phone, I'm actually sending out a stream of zeros and ones out to somewhere, and somebody somewhere is responding to me with a stream of zeros and ones. So how do we convert these radio waves into zeros and ones? So let's see that here. So imagine you have this repeating waveform. And let's say you want to transmit a stream of 0, 1, 0, 1. So what you do is, in the simplest method, what you do is, you either transmit nothing when you want to send 0, or you transmit that same frequency sine wave when you want to send 1. So 0, 1, 0, 1. So that sort of, that's how you send out information. So there are equipments which can do that. This is the most basic form of digital communication. So whenever you're taking your mobile phone to send some WhatsApp message or watch some YouTube, your mobile phone is doing maybe an advanced version of that thing. So that's called modulation. Okay, you're with me? Okay, that's called modulation. And different modulation schemes have different names. I'm only going to say the name of one. The most simplest one is binary amplitude shift keying. It's binary because you're dealing with zeros and ones. You are doing amplitude shift keying. Either the amplitude is 0 or there's some amplitude value. So you're shifting the amplitude. So this is the most simplest one. And you see, you can only send 1 bit at a time. Whenever you're using this one, you can send 1 bit at a time. Imagine the old dial-up modems and very old internet connections which take ages to connect, and it takes ages for you to load some pages. So those guys will be using things like that. But as time, over time, people wanted more data, right? You wanted to watch HD videos, ultra HD videos, 8K videos. You want to do all your mobile. You want to simultaneously browse, be on Facebook, watch YouTube. That means you need more. You should be able to transmit more data at the same time. So how do we do that? So they have more complex modulation schemes, right? So here you can transmit only 1 bit at a time. In other schemes, that increases. See. It's 4 here. I've only shown up to 4. There are schemes where you can transmit 16 or 64 or even 128 bits in one single time frame. So instead of sending 1 bit, you send 128 bits. So that's a very complex modulation scheme. But why are we doing this? We do this because we want to use the available radio spectrum as efficient as possible. Because in the previous slide you saw the radio spectrum is only from here to here. So let's say 1 hertz, 2 hertz, 3 hertz, up to 300 gigahertz. And beyond that, it's not radio. So if you want to use radio efficiently, so you should be able to squeeze in more bits into the available bandwidth. So squeeze in more bits. That's what we are trying to do here. Again, this table, keep this in your mind. I'll tell you later why we need that. Continuing, these are some of the applications. So let's do a quiz again. Can someone tell me what that is? Let's say that one. Yes, that's a radar. This one? That's not a radar. Okay, yes, that's a radio telescope, right? That's a radio telescope. That one? That's a satellite, yes. And that one? Microwave. That one? Bluetooth. Everybody has something Bluetoothy these days, right? This one? Wi-Fi. So that one, a soldier carrying some radio equipment to communicate to his colleagues or his seniors. That's again RF. So, and some sort of wireless sets. Your car keys, car entries, door entries, everything works on radio these days, right? Commercial aircraft, aviations, pilots talk to their air traffic controls using allocated radio spectrum, radio, FM radio, and amateur radio. So what I'm trying to say is this slide shows lots of applications which are utilizing radio spectrum, right? So what does that mean? That means we are actually using too much of radio. There is no more spectrum left for newer applications. That's the point. So if you want to do, tomorrow you are inventing a new device and you want that to be wireless, what spectrum are you going to use? If you're going to use the spectrum of microwaves will not work. If you're going to use a spectrum of, let's say, car keys, whenever you try to use your device, your cars will open, right? So that's a problem. So let's see that further. This is a chart. This is generated by FCC. FCC is the agency who deals with allocating radio spectrum for applications in US. So in UK we have Ofcom, and in different countries have different agencies. So these agencies decide who uses what. So if you might have heard of things like spectrum auction, or mobile companies paying billions of dollars to get a license of certain spectrum usage, TV companies. So all that's done by these sort of agencies. So this is so here it's 0 hertz, and here it's 300 gigahertz. You can see how compressed and how populated the spectrum sheet is. Most of the spectrum is used up. If I zoom it further, so this is, I think I zoomed in one portion. You can see some of them are even sharing the spectrum. So there is not enough no spectrum for newer applications. So tomorrow, if they come up with something like 16K, I don't know, 16K super ultra HD TV format, and if you want more spectrum to send that data, you don't have it here. Either you be clever and invent some new form of modulation where you can squeeze in more bits, or you use something else other than radio, right? So radio is all used up. That is a problem. That is what I'm trying to highlight. Okay? So far okay? Right. And that problem is here. So this is a chart. This comes from a company called Cisco. So they do their annual study to see how much data are people going to use every year. So this is a prediction. You can see it's an exponential increase over probably like 3-4. This is till 2018. So every year you can see that the amount of data is going to, this is in exabytes. Exabytes. 1 exabyte is equivalent to probably 1,000 million movies. If you think about a movie, like a one DVD or something, if you take 1,000 million DVDs, that's equivalent to 1 exabyte. So every this is per month, right? This chart is for a month, per month. And you can see that exponential increase. So people need more data. And these companies always come up with some interesting services which will make us use more data. And here, this chart relates to the previous smaller chart I showed you. How many bits you can squeeze per your hertz. So if you can squeeze more bits, that means more data. You can see that. So in this one, the x-axis is the modulation scheme. So we saw up to 4 before. So this is a different number on the y-axis. Forget that. But you see that this chart is stopping up. This chart is like flattened. It has almost reached a plateau. It's not increasing anymore. That means our technological advancements are not going to help us get more data by using something clever, right? So we have used almost all the radio spectrum. No new innovations are coming up for us to squeeze in more data, and people still wants to use more data. So you see the problem here, right? So how do we solve it? So okay, and one more summary slide here. So different communication systems, we saw some wired ones, copper fiber, waveguides, wireless ones, radio, infrared, sound. These are different wireless ones. Now continue. Okay, so one solution is, can we use this part, the visible spectrum, for wireless communication? Is it possible? So let's compare this both this radio and visible, right? So radio frequencies extends from 0 to 300 gigahertz. So that's 300 gigahertz. So don't worry about that giga number. Just think it of as a big number. 300 gigahertz. Giga means it's like a billion. 300 billion cycles per second, right? Now think about visible. Visible spectrum extends from 450 to 750 terahertz. Tera is 1,000 giga. So it's like 1,000 billion, right? So if you compare the bandwidth, the visible bandwidth is 300 terahertz. Why does this look so small and this so big? Because this is a logarithmic scale, right? It's a logarithmic scale. So when you put things on logarithmic scale, it compresses. That's for easy viewing. And the spectrum available in visible is 1,000 times more than what we have in radio. So see the point here, we can use visible if technology allows for wireless communication, and we have 1,000 times more spectrum there. So let's see what happens. So now we have a new entrant. So we discussed, okay, we are using radio so far, we are good, all our services are being satisfied, but all the spectrum is used up. In future, we might need something else, and one of the solutions is light, right? And researchers have been working in this for some time, and a term exists for this tech. This is the name for this technology. It's called Li-Fi. So if you think about Wi-Fi, which is wireless fidelity, this is Li-Fi, which is light fidelity. Okay, so that's a technology that I'm going to talk further. So far we have discussed the radio, how radio evolved, how could we transmit information, what are the disadvantages, and how can we solve it. So that is using light. So this is a bit more history about this. Again, we saw Graham Bell picture some time ago. This is again Graham Bell. Graham Bell's first, he thinks his most important invention was something called a photophone. So that was the world's first light-based wireless transmitter. He did that like 120 years ago. So it's a patent 1880 by Graham Bell for photophone. So what he did was, he wanted to transmit sound waves wirelessly. So he did some optics. He could shine light into a mirror, and to the mirror he attached a mouthpiece. So when you talk into the mouthpiece, because of the force of the air coming out of your mouth, it rotated that mirror. and he could transmit that information to probably 100 meters or so and get it back. So that was the world's first visible light communication system. But it didn't take, after that it was not taken. But the reason is there was the technology required to make it sustain was not there. So the concept was demonstrated long time ago by Graham Bell himself, and he said that was his most important invention. But it was not taken further. The nearest brother to this sort of technology is remote control. But that was there since 1955. If you remember your TV remote controls, if you press a button, it changes channel on the TV. In front of your remote control, there is an infrared LED. Infrared is light, but you can't see that. Only thing is your eyes are not sensitive to that. But when you press the button, it sends out a stream of bits to the TV, which TV receives. So this was, again, a very old system existing since 1955. Now how does Li-Fi work? So what we do is, see these bulbs, light bulbs above you. Assume these are light bulbs which I can turn on and turn off, right? So what I do is, remember we saw sending, how can you send out 1 and 0? Binary 1 and 0, you turn off and turn on. So if you turn off your light, you're sending a 0. If you turn on your light, you're sending 1, right? I can show it to you. Let's say I take my mobile phone's torch. So this is the most simplest Li-Fi demonstration. See, I've turned on my torch, turned off, turned on, turned off. So that's sending out 1 and 0. That's the most simple demonstration. But if I do it in that speed, that won't be enough for you to watch your YouTube videos. You need to do it much faster, right? How fast? You need to do it millions or trillions of times per second, right? Can you do that? You can, of course, you're dealing with things which are millions and trillions of which goes at that speed. If you think about a mobile phone, if you read their specifications, you will see this mobile phone will work at 2 gigahertz. That means it's already switching at that speed. So we have the technology to switch things at that speed, but we don't have bulbs which can be switched at that speed. That's the problem, right? So the problem with one of the hurdles was, how can you switch on and off a bulb millions of times a second? If you think about the bulbs you see here, there are 2 types. It can either be incandescent bulbs or fluorescent bulbs. So how does incandescent bulb produce light? What happens inside that bulb? So what it does is, when you supply a voltage, a current will flow through the filament, and the filament heats up. It takes time to heat up. It's a tungsten filament. It takes probably a few milliseconds to heat up. Once that filament heats up, it emits light. So that takes, in a second, if you try to switch on and off, this bulb will probably, you can turn it on and off probably like few times, maybe like 10 times, right? It's very slow. And same for the fluorescent bulb as well. So that can also be turned on and off only for a few times. So that's a problem with these bulbs, which we had so far. So that was the limitation which Graham Bell faced. He did not have a bulb which can be turned on and off so fast so that he can send his audio or voice or whatever to long distance. But now we have a different bulb, right? Everyone might be heard of LEDs, right? And LED stand for a light emitting diode. So in the previous bulbs we have seen, they do not convert electricity to light directly. They convert electricity to, in this case, they convert electricity to heat, then heat to light. In this case, it's a process of phosphorescence. So that's another way of emitting light. In both cases, you lose lots of energy. When you do this, you lose lots of energy. In the case of LEDs, what happens is, LEDs convert electricity to light directly. That's why they say LEDs are efficient. That's why when you go to a shop, they say LEDs are greener, LEDs are efficient, because they convert electricity to light directly without any intermediary. There is no heat involved. So how does that work? This diagram is a bit complicated, but I'm going to explain to you, hopefully in an easy way. Let's say this is an LED, right? That's an LED. What happens is, let's say you take an LED, you put a battery and connect to the LED. So there will be a positive terminal and a negative terminal. And from the battery, the current flows. So the current has to flow through this thing. So LED is made of a special type of material called semiconductor. If you think about semiconductor, it is something which conducts electricity, but not as good as a metal. If you compare the conductivity of a copper and an LED, the conductivity of copper is always higher than that of semiconductor. It's made of, it's actually glued, two different types of semiconductors glued together. One has lots of electrons. Electrons are negatively charged, and the other one has less electrons, right? So one has lots of electrons and less electrons. So when you connect a battery will attract electrons. One terminal of the battery will attract electrons, and the other terminal will repel electrons. So there will be a flow of electrons going like that. So whenever there is a flow of electron, it reaches this junction and it emits light. How does it emit light? It's like, you can think it of like this. Imagine these electrons are walking, and suddenly there is a deep well, and the electrons will fall into the well, right? When the electrons fall into the well, electrons already had some energy, but when it fall into the well, it loses its energy. If I take this pointer, if I bring it at this height, it has certain potential. So that's the potential energy of this thing. If I leave it, its energy is lost. Not broken. So that's some basic physics, right? So what happened here? You have lifted it. I used my energy to lift it up, increase its potential. I brought it to this potential. I just leave it. It falls down. It loses that potential energy. How does it lose it? It loses it as kinetic energy. Some of it becomes sound when it hits the ground, right? So that is some basic physics. Similarly, electrons are walking. It reaches a potential well. It just falls down. When electrons falls down into a well, it loses whatever energy it has gained earlier. And when it loses energy, energy has to go somewhere. So that energy comes out as light, right? Photons. So these electrons will emit photons from the junction when it falls into the well, right? That's the most simplest explanation I think I can give, right? So it's semiconductor, it has electrons and holes. When you apply a voltage, these electrons and holes are wells, they recombine and they emit light, right? So this is direct electrical to light. There is no heat here, no infrared or no phosphorescence, right? And it can be faster. So this device can be turned on and off much faster than the previous bulbs we have seen. Then some cool tricks, right? So if you think of this lights above you, okay, let's think it like this. We have evolved beneath the sun. So we prefer sunlight, right? So we always like a yellowish light. We do not like too much white, or we do not like colored lights. That's why all the indoor lighting or whatever lights you see, sodium vapor lamps, all have, human beings prefer a slightish yellow light, which has some, they call it a color temperature. So some higher color temperature, right? So we can produce these sort of different colors using different color LEDs. If you take a red, green, and blue, if you just mix the light, you get white light. And if you adjust the current going through each of those LEDs, you can adjust the color temperature. So you can also get yellowish light from this sort of setup. So what that means is you have 3 different LEDs and 3 different channels. So assume 3 people are here using their mobile phones, and there's a white light above you, but the white light is actually a mix of 3 different colors. And 3 people are browsing 3 different, they are using their mobile phones. So one will be connected to red, one will be connected to green, and one will be connected to blue. What's the advantage? There's no interference. Each of them have their own channel, and it'll be faster. But if you're using the Wi-Fi in this room, everybody is sharing the same Wi-Fi. So that'll be slower. So compared to that sort of arrangement, if you demultiplex like this, you will have a faster data link, right? So these are like some sort of artists, what do you call it? Expression of how it works. So you can have different light bulbs. These light bulbs can be linked to different functions, including let's say your computer, your mobile phone, your laptop, or even your thermostats or whatever they are, your projector, right? In a meeting room, right? If you want, you don't need to share your Wi-Fi channel. So let's say there are 50 people in this room. Everybody is trying to use Jurisin's Wi-Fi router fitted somewhere there. The per person bandwidth is reduced, it's divided, right? But in this case, you can feed each of them with much higher data rate. So there are some of the pros and lots of misconceptions. So let's talk about the pros first. First of all, as I'd shown before, the visible spectrum is 10,000 times more than the radio, so much higher bandwidth. And it's non-regulated, right? Nobody is regulating light. Ofcom is not going to regulate how much light we are going to get, right? At least now, or maybe even in near future. Nobody is going to regulate light. So light bandwidth is not controlled. It's energy efficient because you already have these bulbs there. They already give you light. So what if you add an extra circuitry or extra setup to give you a bit of data? That means you don't need to install no Wi-Fi routers. You already have the infrastructure there. Next one is no interference from RF, right? This is one of the main things. If you think about RF, let's say there are like 10 people having sky routers in, let's say, in an apartment complex. The Wi-Fi will interfere and your data rate will come down. You can try that at your home. If you see that the number of Wi-Fi routers in a restricted or in a specified area increases, the amount of data you get reduces. That's because there will be interference. In the case of light, there's no interference like that. Next one is, okay, this we already discussed, existing infrastructure. And high security. The light from this room is not going to the other room. So but the Wi-Fi from this room will always go to the other room. That's because radio waves have longer wavelength. They can actually go around obstructions, right? So if that's like sound. If I'm talking here, the person next to might be able to hear it because sound waves have longer wavelength. It can go around obstructions, but light can't. The wavelength of light is smaller. That means it cannot go through that door. So it's yes, that's possible. It has higher security compared to RF. One point I missed is safety. You cannot use your radio waves or radio links in many places. If you go to a petrol station, you will see a sign saying, please turn off your mobile phone. Why do they say that? Anybody knows? Why do they ask you to turn off your mobile phones on petrol stations? Yes, it can cause antenna sparks, right? So whenever you're trying to use a mobile phone, your 5G or 4G antenna is active, so there are chances of sparks, and if there are chances of sparks, that'll be a problem in a petrol station. So in such places, light-based wireless communication can be useful because light will not cause spark when you use it. Some misconceptions, right? So people usually ask, can you turn off the light or dim the light? Will it still work? Of course, if you turn off the light, it will not work. But if you dim the light, it will. The thing is, the speed might go down, right? So that's one thing. Then lights flicker. So I said you need to turn on and turn off. So if you're turning on and turn off millions of times, if you look at that, oh, what's that? Will that happen? No, it won't happen because your eyes can only see switchings up to 25 hertz or 25 times a second. That's your TV screen's minimum refresh rate. If anything switches above 25 times, you will not see that, right? So your perception, so you will not perceive that as a flicking thing. You will see that as a constant light. Next thing is only downlink. Can you use this for uplink? So for example, you have lights on your ceilings, but do we need lights on your mobile phone? Yes, you can use it for uplink, right? Next one is sunlight's interference and line of sight. So will it work if I'm on another room? No, it won't work. But you can always think of if you put your mobile phone under your chair, will it work? Yes, it will work. It can actually get light from reflected places. For example, you can see that underneath the chair, it's already lighted. That's because of reflection. So it can still work in such places. How much intensity is needed for good transmission? That depends on the application and how much power you're emitting. So that's the thing. It's proportional to the power. So if it's too much powerful, yes. So if I put it here, yes, good reception. If I move there, it might reduce. It's the same as Wi-Fi. Some of the applications of Wi-Fi, these are specific applications. For example, you know that we have street lights everywhere, right? So they can be converted to access nodes or data points. And car to car, every car has a tail lamp and a headlamp. So cars can communicate with each other, right? Making a smart, transportation network if needed. Petrol stations or oil refineries. Nobody is allowed to use RF on oil refineries, but light-based, yes. Underwater. So it's very difficult to communicate to a submarine because you need very low frequency radio. That's one problem, but you can use light there. Then these are some of the other smart applications. I'll tell some, I'll say, all devices have LEDs, microwaves, water heaters, washing machines. Everybody has an LED at front at some point. So they can be used to send some information. Let's say how much power I consumed, right? How long was I turned on? Things like that. Indoor navigation, right? You can use this to navigate inside a big building. Museums, so advertisements, lots of other applications. These are some of the demonstrators that I did as part of my PhD. There's one short video. Let me try to play that. So that's what you see there. It's a microchip with some micro LEDs. These are very small LEDs, not the ones we buy from B&Q. These are 10 micrometers or smaller, but they can be used for short-range optical communication. For example, to realize a short-range data links. Just if you want to have a docking station to send data to your phone, you can use that. Yeah, that's all. Thank you very much. Happy to take questions if there is time.